Hello there, Mr. Sutton bringing you the AB Calculus 414 homework solutions on basic related rates. For number 1, we have the area of a circular region increasing at a rate given here. When the area is a certain amount, how fast in meters per second is the radius increasing? So let's start with the formula that ties all this together. This is, by the way, is a related rates problem because we have the rate of the area and the rate of the radius, multiple rates of change. So area formula for a circle would probably be a good place to start. A equals pi r squared. And let's go ahead and take the derivative of everything here. So that'll be dA over dt on the left. And we're taking the derivative of everything with respect to time. So we've got then 2 pi r dr over dt on the right side. And let's take stock of the information that we have here. So ultimately, we wanted to know how fast is the radius increasing. So we're looking eventually for dr over dt. That means we need to find values for dA over dt and r. dA over dt, that's the rate that the area is changing at. They gave us that, 96 pi square meters per second. So we'll just make a note of that. We do need the radius, though. They did not tell us what the radius was. So we need to use the area that they gave us here to figure out the radius. We already have a formula for area in terms of radius. So let's just do 64 pi equals pi r squared, and then we can solve for the r in this problem. Dividing by pi, we've got r squared equals 64, and then if we square root, that means r has to be 8. 8 meters if we're being specific. All right, so let's plug the r in with the 96 pi. So we've got 96 pi equals 2 times pi times 8 times dr over dt. And at this point, we're just dividing step by step to solve for dr over dt. So if we divide by 2, that's going to be 48. We can divide the pi's away. 48 divided by 8 is going to give us 6. So we have 6 meters per second then for the rate at which the radius is changing. Choice A. For number 2, they're telling us when x equals 8, the rate at which the cube root of x is increasing is 1 over k times the rate at which x is increasing. What's the value of k? Well, let's start with figuring out the rate, general rate, at which cube root of x is increasing. Cube root of x, that's really the x to the 1/3. So derivative of that is 1/3 x to the negative 2/3. And now they're telling us that when x is 8, this rate of change should be 1 over k times the rate that x is changing. Okay, well, let's plug in 8 for x and then just set that equal to 1 over k. So if I do that, I'm going to also make this in fractional radical kind of form here. So I can write 1 over 3, and then I'll have the cube root of 8 to the second power. All of that should equal 1 over k. All right, so let's just solve for k now. So I've got, let's see now, this is going to be 2 squared is 4 times 3 is 12. Well, if 1 over 12 equals 1 over k, then if you cross multiply, that means k equals 12. Choice E.
For this problem, we're told the fuel consumption of a car in miles per gallon is modeled by this f of s function, which is kind of crazy looking. And s is the speed of the car in miles per hour. If our car is traveling at 50 miles per hour and the speed is changing at a rate of 20 miles per hour squared, we want to know the rate at which its fuel consumption is changing. So basically, we're trying to figure out df over dt. That's what our goal is here. The only catch is that we have two things going on that we would have to plug in. So, because we've got the rate at which the fuel is changing, but we also have the rate at which the speed is changing. So we have two different rates of change involved in the same problem. So this is actually a related rates problem, and we're going to have to implicitly differentiate everything right at the very beginning to access that speed rate of change of 20. So let's go ahead and take our derivative. So we have df over dt, and we're also going to have the derivative of all this stuff with respect to time. So initially we have 6e to the something here. This is kind of a big chain rule going on. But now we have to multiply by the derivative of the something, of the exponent here. So first we have the derivative of s over 20. That's like having 1 over 20 times s. So that derivative is just going to be 1/20th. But because we're differentiating with respect to time rather than speed, we actually have to have a ds over dt tail, because we're treating speed as an inner function in this problem. And next we're going to do this s squared over 2400. So using our power rule, we have 2 times 1 over 2400. We can reduce that to negative 1 over 1200. And then we have s to the first power. And again, we differentiated something with an s, so we need a ds over dt tail for that inner function. So this is the whole derivative. Now we have to plug some things in. So for s, we're going to plug in the 50. That's the actual speed of the car. So we have 6e to the 50 over 20 minus 50 squared over 2400. And we're going to have 20 going in for the ds over dt. And just to verify, this is a positive 20. They said we're changing in a rate of positive 20, so that's what we'll plug in. So we have 1 over 20 times 20 minus, and now we're also going to have, let's see here, negative 1/1200, s is again 50, and we've also got 20 going in for ds over dt. So at this point, I'm going to try to put all this into Desmos and come up with an answer. So we've got 6e exponent, and lots in this exponent, so I'll use a parentheses here. We have 50 over 20 minus, and I'll do another fraction here, 50 exponent squared over 2400, and let's close that parentheses. Let's go down to the non-exponent level now and open up another parentheses, and I need to move this so I can actually see what I'm doing here. So we have 1 over 20 times 20, which I know is 1, but whatever. I'm writing things out as much as I can. And then we have 1 over 1200 times 50 times 20, and then close all that. And it comes out to about 4.299. And the units on that is going to be, well, let's see, the rate at which the fuel consumption is miles per gallon. So the rate at which that consumption is changing is going to be miles per gallon per hour, mpg per hour. So 4.299 mpg per hour. That's a weird unit, but there you go. And then that's going to give us answer choice B.
For number 4, we have a cube with edges of length x centimeters with a volume of x cubed cubic centimeters. Volume's increasing at a constant rate of 40 cubic centimeters per minute. At the instant when x equals 0, what's the rate of change of x with respect to time? So this is a related rates problem. We have multiple rates of change of volume, of x, and we want to figure out the rate of change of x. So let's take the derivative of the volume formula here with respect to time. So we'll have dv over dt on the left equals 3x squared dx over dt on the right. Let's plug in what we know. Volume is changing at a rate of 40 cubic centimeters, so we'll plug in 40 for dv over dt. And x, they told us, was 2 at the instant we care about. So we're just solving for dx over dt then. So I've got, let's see here, 3 times 4, so 12. So dividing by 12, we've got 40 over 12, which we can reduce to, let's see, dividing by 4, we've got 10 over 3. So 10 over 3 centimeters per minute, and that'll be choice A. Number 5 is an interesting problem. We have the radius of a circle increasing at a non-zero rate, and at a certain instant, rate of increase of its area and circumference are going to be numerically equal to each other. We want to know what the radius of the circle is at this instant where those two rates of change happen to be the same. So this is clearly a related rates problem. You have all these different rates of change going on at once. We also have two different kind of formulas that tie this all together with the area and the circumference. But there's nothing that links those two together directly. It's their rates of change that are the same. So let's start by writing the area and circumference formulas. We've got area equals pi r squared and circumference equals 2 pi r. Since it's their rates of change that are the same, let's go ahead and take the derivative of both of these with respect to time. So for area, we've got dA over dt equals 2 pi r dr over dt. For circumference, we've got dc over dt equals 2 pi dr over dt. And they told us that dc and dA over dt were the same, so that means that 2 pi r dr over dt and 2 pi dr over dt also have to be the same. Now they wanted us to solve for the radius of the circle at this instant. We're solving for r. So let's start dividing. With these 2 pi's can cancel out, so we just have r times dr dt equals dr dt. Now, it'd be nice if we could divide by dr over dt, but we might hesitate a little bit because that is technically a variable, and we've been told we're not supposed to divide by variables because we might be dividing by 0. If we read back in the problem, however, it says the radius of the circle is increasing at a non-zero rate. They're telling us that dr over dt is not 0, so we can actually divide by it. So we've divided away everything. We just have r equals 1 then. Choice D. For number 6, we have the radius of a circle increasing at some rate. We want to know the rate of increase of the area of the circle when the circumference is a certain amount. This is related rates. We've got multiple rates of change, and we're looking for the rate at which the area is increasing. So let's start by writing the area formula for a circle. A equals pi r squared. We're now going to take the derivative of both sides with respect to time. So we'll have dA over dt equals 2 pi r dr over dt. And we need to be able to, again, solve for dA over dt. So that means we need to have some way of representing r and dr over dt. So what did they give us? They told us that the radius of the circle was increasing at 0.2 meters per second. So for dr over dt, we'll plug in 0.2. Now how about for r? They did not tell us the radius. They did tell us the circumference. Now before you go ahead and plug this in for circumference and back solve for r, take a look at what you have here. 2 pi r. What's another name for that? Oh yeah, isn't that the formula for circumference itself? So if they're telling you that the circumference of this thing is 20 pi, then you can actually replace this whole 2 pi r expression for 20 pi. So then we'll have 20 pi times 0.2. Well, 0.1 of 20 would be 2. So 0.2 of that's going to be 4. So we have 4 pi total for that one. And that's going to be meters squared per second, because this is the rate of change of the area of the circle. So that was choice C. For number 7, base of a triangle is increasing at a rate of 3 inches per minute. Its height is decreasing at the same rate. Which of the following must be true about the area of the triangle? So we're talking about area always increasing, decreasing under certain conditions, constant. These are all talking about the value of A prime. So with these related rates going on, let's just set up the area formula for a triangle and then take the derivative of everything with respect to time and see if we can sort this out. So we've got A equals 1/2 base times height. And again, I'm going to take derivative with respect to time because I'm seeing these different rates of change. This is telling me it's a related rates problem. So we've got dA over dt equals, and then let's do a product rule for that right half. So we've got a 1/2 b and an h. So I'll do 1/2 dB over dt and dH over dt. I've got my box. Using my ribbon now, I've got 1/2 dB over dt times h plus 1/2 b dH over dt. All right, let's plug in the information they gave me. They said the base was increasing at a rate of 3, so we'll plug in positive 3 for dB over dt. They said the height is decreasing at a rate of 3. So we're going to plug in -3 for dh over dt. They didn't tell me anything in here about the height or the base of the triangle at a specific time. So we're going to have to leave those as h and b for now. Really, all I can do at this point in the problem is try to factor out some things and clean this up a little bit. I mean, you could try to analyze this and looking at the answer choices without simplifying, but it's going to be a much tougher thing to do. So I can factor out a 3/2 from both of these. That'll leave me with h minus b inside of parentheses. And if I look at it this way, it's going to be a little bit easier to do some sign analysis on a prime. Let's look at our answer choices now and see if we can shed some light on these. First possibility, a is always increasing. So they're saying that a prime is always going to be positive. Well, 3/2 is positive, but h minus b is not always going to be positive. What if b is larger than h? So we can cross out choice A. Choice B, A is always decreasing. We don't know that A prime is always going to be negative. What if H is greater than B? So that's not a good one either. And then the easier one to eliminate out of the rest of these is this choice E, A remains constant. That would be if this stuff came out to 0, but that only happens if H and B are the same value, which is not guaranteed. So we have to go with these conditional answer choices. One possibility, decreasing if b is less than h. Other possibility, decreasing if b is greater than h. Well, let's look at this here. If b is greater than h, then a prime is going to come out negative. So that's going to give us answer choice D out of those two.
On this problem, we have the volume of a sphere decreasing at a constant rate of 3 cubic centimeters per second. At the instant when the radius of the sphere is decreasing at a rate of 0.25 centimeters per second, what's the radius of the sphere? And they gave us the volume formula for a sphere, 4/3 pi r cubed. Very nice of them to provide that. All right, so we've got multiple rates of change happening. We have the rate at which volume is changing involved in this problem, and we have a rate, we're talking about the radius of the sphere having its own rate of change. So this is a related rates sort of problem. We're going to start with a formula that ties in all the different quantities, which is this volume formula, and we're going to implicitly differentiate this and then figure out what we're actually solving for. So let me take the derivative of this whole thing, and these are all changing with respect to time, so I'm going to differentiate all of this with respect to t. So the derivative of v, I'm going to call that dv over dt when I take the derivative of this formula. And now I'm also going to take the derivative of the right side. So this is a power rule going on. We have 3 times 4/3 pi. The 3's cancel, so we just end up with 4 pi r squared. But since I'm differentiating with respect to time, I need to add a tail of dr over dt, because the radius, like the volume, is its own kind of inner function. All right, so let's see what I can plug in here. So they told me the volume of the sphere was decreasing at a rate of 3 cubic centimeters per second. So I can replace dv over dt with -3. And then they were actually asking us to solve for the radius. So the 4, the pi, the r squared, all of that is going to stay where it is for now. Going to solve for r eventually. And then for dr over dt, they said the radius of the sphere was decreasing at a rate of 0.25 centimeters per second. So we'll replace that with -0.25. And now we're just going to simplify this and solve for r. So let's see. We got 4 times basically -1/4, which is going to be -1. So I can write this as -pi r squared on the right side. Next, to get r by itself, I need to divide both sides by -pi. So I've got 3 over pi then if I get rid of those negatives. And I also, to get rid of the square, need to square root both sides. Since radius should only be positive, I don't need to do the plus or minus square root, just the positive root. At this point, though, in order to match an answer choice, unless you know what this is off the top of your head, we need to plug this into our calculator. So let me go to Desmos for that. It's kind of overkill, but we'll do it. So let's do square root sqrt. And then we've got 3 divided by pi, pi, is what you need to price to get that. And that comes out to 0.977. And that's the radius, so that's going to be in centimeters. And that's going to match up with answer choice E.
For this problem, we have a spherical snowball melting in such a way that it maintains its shape and decreasing in volume at a constant rate of 8 cubic centimeters per hour. They want to know the rate in centimeters per hour that the radius is decreasing at the moment the radius is 10 centimeters. And they gave us the volume for a sphere right here, so that might be useful. So we are given the rate of change in volume, and we want the rate of change of the radius. This is a related rates problem where you have one rate of change and you need another rate of change. To solve this, we're going to start by rewriting this formula that they gave us, because this handy-dandy formula includes the original quantities that we're going to get both of those rates of change out of. So we've got dv over dt. We need to find dr over dt, essentially. To get access to those, we need to differentiate this whole equation implicitly with respect to time. So on the left side here, the derivative of v with respect to time is just dv over dt. And now on the right side, we'll use our power rule. So we have 3 times 4/3, which is just 4, times pi times r squared, times dr over dt. All right, what did they give us? Well, they gave us this 8 cubic centimeters for the dv over dt, the rate of change in volume. It's decreasing by 8 centimeters, so that's going to be -8 that we're using for dv over dt. And they told us that they want dr over dt at the instant when the radius is 10 centimeters. So we have an instant value of r equals 10. All right, let's plug all this in and see what dr over dt equals. So rewriting all this now, we've got -8 equals 4 pi times 10 squared times dr over dt. And there's no calculator allowed on this one, so I'm going to divide this in pieces here. First off, -8 divided by 4, that's -2. And then I'll divide by this 10 squared. So far I've got -2 over 100. And then, let's see, that reduces to -1/50th. Divide by pi, I've got -1 over 50 times pi. Now, you might look at the answer choices and be like, well, hey, there's no -1 over 50 pi. But if you reread the question, they want the rate at which the radius is decreasing. Well, we've got a decreasing rate of change here because it's negative. The rate at which it is decreasing, they're just asking for the absolute portion of this, which is 1 over 50 pi, choice A. For number 10, volume of a cone of radius r and height h is given by this formula here. That was nice of them to tell us that. If the radius and height both increase at a constant rate of 1/2 centimeter per second, at what rate in cubic centimeters per second is the volume increasing when height is 9 and radius is 6? So we got a whole lot of information here, and we're going to need it. A whole lot of rates of change going on, so this is a related rates problem. We're going to start by differentiating with respect to time. To do that, I am going to need to use a big old product rule on this. So for one of these, I've got 1/3 pi r squared. And for the other one, we've only got h. Derivative of this first one, this is going to be 2/3 pi r times dr over dt. Don't forget that tail. And over here, we've got dh over dt. Using my ribbon to multiply this out and add, I've got 2/3 pi r dr over dt times h plus, well, all this stuff. 1/3 pi r squared times dh over dt. All right. So at some point, I'm going to have to plug in some numbers here because ultimately I wanted to find, what did I want to find? The rate at which the volume is increasing. So we need dv over dt eventually. So let's see if we can figure out what all these are. We've got r. They did tell us that the radius was 6 centimeters, so 6 for r. dr over dt, well, they told us that the radius and height were both increasing at a constant rate of 1/2, so that's 1/2. H, they told us, that was 9. And there's r again, 6 squared over here. dh dt, that's going to be 1/2. So plugging all that in, we just have to crunch these numbers out a little bit. Now, if you look at the answer choices, these are all in terms of pi, so we just have to simplify it with pi on it. taking a look at this first fraction, I've got, let's see, half of 6, that's 3. 3 times 2/3 is 2. 2 times 19 is 18, so we have 18 pi. Over on this next one, I have, let's see, 1/3 and 1/2. That becomes 1 over 6. Times 36 is just 6. So we have 18 pi plus 6 pi. That gives us a grand total of 24 pi. So that's going to be choice C.